The repeating faces and sharp angles of mineral crystals have fascinated observers for millennia. In Greek antiquity, this flawless regularity helped form our earliest concepts of atomicity and the geometric structure of matter. We now know this macroscopic beauty is a direct manifestation of microscopic regularity. This diffraction pattern, made of discrete spots of reflected X-rays, provides the actual proof that the atoms inside are arranged in a perfectly repeating grid. Crystallography has moved beyond minerals and into biology. Since the 1950s, we have used these same principles to determine the atomic structures of proteins, providing the blueprints for modern structure-guided drug discovery. There is a practical hurdle, however. X-ray diffraction only works on a periodic lattice. To see a protein, we have to force millions of individual molecules into a rigid crystalline assembly. Unlike the simple atoms in a mineral, proteins are large, flexible, and completely irregular in shape. They possess no inherent symmetry. Despite this irregularity, a successful experiment requires these molecules to self-assemble into a flawlessly repeating three-dimensional grid. The real challenge lies in the packing. We have to find a way to fit these asymmetric, messy biological shapes into an infinitely repeating mathematical matrix. If you try to tile a floor with arbitrary, different shapes, the pattern fails. As this diagram shows, the shapes cannot fill the plane without leaving uncovered holes. Successful tiling requires shapes defined by two sets of intersecting parallel lines. These lines form the lattice, the underlying grid that dictates where every piece must go to cover the space perfectly. A lattice is a mathematical construct, but a crystal is a physical one. We create a unit cell by placing our molecular motif inside a lattice tile. Copying and translating that cell across the grid generates a periodic two-dimensional crystal, repeating at regular intervals. This demonstrates that even in two dimensions, the requirement for translational periodicity limits how objects can be arranged in space. In the real world, we have to expand these rules into a three-dimensional matrix. In 3 dimensions, there are only 14 ways to arrange points in a translationally periodic lattice. These are the Bravais lattices, the essential skeletons for any 3D crystal structure. When we combine these 14 lattices with all possible geometric operations, like rotations and mirror reflections, we find exactly 230 unique ways to organize matter in space. These are the 230 space groups. While minerals can utilize any of these 230 arrangements, biological molecules are restricted by a specific physical property that the math does not account for. That property is chirality. Built from L amino acids, proteins have a permanent handedness. Because of this, a protein cannot be superimposed on its mirror image. This handedness acts as a filter. It invalidates any space group that uses mirror planes or inversion centers. Applying those operations would turn an L amino acid into a D amino acid, effectively creating a molecule that doesn't exist in the crystal. With mirrors and inversions removed, proteins are restricted to only 2 types of symmetry: plane rotations and a specialized move called a screw axis. A screw axis is a 2-step operation. The molecule rotates by a specific degree and then shifts linearly. This allows asymmetric proteins to nestle together in repeating helical columns, filling the 3-dimensional space without violating their biological handedness. By filtering out every symmetry move that flips the molecule's chirality, nature has vastly reduced the number of ways a protein can self-assemble. Once you remove the 165 space groups that require mirrors or inversions, you are left with exactly 65 chiral space groups. Every protein crystal ever grown belongs to one of these 65 arrangements. This is an absolute mathematical ceiling. Regardless of the protein's function or the lab conditions, it must conform to one of these 65 structural types to form a periodic lattice. Scientists use this limitation to make sense of complex data. When analyzing thousands of X-ray reflections, they aren't searching for a needle in a haystack of infinite possibilities. They use the 65 space groups as a definitive template to decode those reflections, allowing them to calculate the precise coordinates of every atom in the molecule. This mathematical regularity is the exact mechanism that allows us to finally see biological structures at the atomic scale. By understanding these 65 allow arrangements, we can precisely engineer the advanced materials and medicines we use every day. Deep inside a protein crystal, there is a sprawling thicket of atoms. To us, it looks like chaos, but our brains are tuned to instantly isolate the repeating geometric patterns hidden in the noise. Nature fits these asymmetric puzzle pieces together using exactly 65 discrete configurations, known as chiral space groups, each defined by its own set of rotations and physical shifts. While a scientist can intuitively visualize a shape turning in three-dimensional space, modern crystallography is an exercise in processing millions of data points. This creates a reliance on computational power. Computers are blind to physical geometry. They don't perceive shapes. They only recognize coordinate-based commands. To map a crystal, we have to translate spatial symmetry into the language of matrix algebra. Historically, mineralogists identified crystals by their visible faces. But probing the atomic structure of complex proteins shifted the field from visual inspection to the abstract, data-heavy processing of digital hardware. To function, these machines require a rigorous mathematical protocol that defines precisely how to move a three-dimensional object through space without error. This forced researchers to move past intuitive models and rebuild the geometry of crystals using the logic of linear matrices. If we isolate a single coordinate, point P, and apply a two-fold screw axis, which is a rotation combined with a small step forward, we arrive at a new position, P'. Tracking this movement reveals a specific coordinate shift. The horizontal position, x, and depth, y, both flip to their negative values. Simultaneously, the vertical height, z, increases by exactly 1/2. This symbolic list is easy for a person to read and verify. It is a direct shorthand for the physical movement of the atom. However, high-speed rendering software cannot efficiently process text-based symbols. To calculate millions of atomic positions in real time, the data must be reformatted into a computable operator. This is the matrix operator. It translates spatial movement into a single mathematical command. The R is a 3x3 grid that defines the rotation. It acts on the original coordinate vector to flip or twist the position in space. The T is the translation vector. This adds the final linear step that moves the object forward along a specific axis. By plugging the integers -1 and the fraction 1/2 directly into these grids, the computer performs a single calculation that matches the physical screw axis movement we saw earlier. Complexity is reduced to efficiency. Physical movements are now packaged as unified, repeatable mathematical instructions. To prevent these operations from creating a chaotic sprawl of molecules, crystallographers apply a rule from group theory called closure. Closure ensures that repeated application of these matrices doesn't lead to colliding atoms or infinite spirals. Instead, the operations loop perfectly, returning the molecule to an equivalent position that builds a stable lattice. This mathematical constraint ensures that only physically possible arrangements are generated, turning abstract algebra into a stable crystal structure. The parameters for these operators are archived in the International Tables for Crystallography. This catalog provides the specific matrix values for every known chiral space group. To generate a model, a scientist provides the software with a single molecule and the matrix generators listed for that specific group. Finally, the computer's dimensionless grid is scaled to physical reality. An orthogonization matrix converts the abstract coordinates into the real-world units of angstroms used in molecular models. With the molecule, the symmetry rules, and the physical scale established, the computer can simulate the structure of a crystal with perfect precision. The software executes the matrix math. In fractions of a second, the original molecule is cloned and rotated millions of times across the grid. The result is a massive three-dimensional crystal lattice where every molecule is perfectly interlocked. This chart shows that nature has a massive preference for screw axis symmetry over plane rotations. This isn't random. Screw axes provide a higher number of degrees of freedom, meaning they offer more flexible mathematical ways to connect molecules in a dense, three-dimensional network. By translating physical shapes into matrix algebra, we reveal the underlying logic nature uses to assemble its most complex structures.